So the goal of this video is to train our neural network on this particular data. Now what is this? Can you recognize this? Yes, this is XOR logic gate, exclusive OR. Now, how a neural network is different is, we don't write rules to the machine and we don't describe how an XOR works. We'll just provide the data, the inputs and the target values, and the machine will learn on its own. That's the whole idea, or that's the whole goal of this particular video. We'll also write the code and we'll let the machine learn XOR. We'll let the machine learn this particular pattern. Now let's start from the basics. Let's start with the term when we hear neural network. I just quickly search neural network on internet, and what I see is like, let's say on this particular image, right? I see so many layers, like input layer, hidden layer, and an output layer, and so many connection and edges. Well, these connection definitely describes that, okay, this is some sort of network, right? And also I see some bubbles, and they call it neuron. Now what is neuron? Now you might have heard this term from biology. So a neuron, as you can see, is the core building block of a human brain and our nervous system. And why they took this term is because the framework or the architecture sort of resembles neuron from the biology. So this is the neural network. Now let's get the understanding of how a neural network works. How does a neural network learn? What does training mean? So for that, I'll play a quick video and I'll also explain you things side by side. So what I want you to imagine, imagine neural network as a guessing machine. So we'll give some numbers as input and it will guess some number as an output. So numbers in and numbers out, and it will guess. At the starting, it would be an absolutely random guess. Now see here, we have a cat image and we have converted that image into numbers. We give that as an input and we let the machine guess. And let's say our network says, oh, it's a dog. But we know it's wrong, right? So we have to calculate how wrong it is. So we call it a loss function. What is loss? Loss is basically the difference between the machine's guess and the correct output. Now, in order to make the output better or machine's guess better, we have to nudge certain values. So we'll go back into our network and we'll change the weights and biases. Now you'll be wondering, what are these weights and biases? I'll come to those in a minute. So right now what you need to understand is we calculate loss, which is the difference between machine's guess and the correct output. And the ultimate goal of our network is we have to minimize this loss. That's the whole game. That's the whole thing that we are dealing with. And you can see that we will definitely need some calculus, a bit of differentiation here in order to minimize this particular function. Don't worry, it's going to be easy. I promise that. So what's the whole game? The forward pass, as you can see, in forward pass, machine makes a random guess. Then we measure the loss and then we go back into our network and we nudge certain values. And we repeat this process again and again and again, right? So this was the overview framework of how a neural network learns. Now, let me tell you, what does learning mean? When we say we are training a neural network, what does it mean? So as I mentioned, when we come back, we nudge certain values. Now those nudges has to be smartly done. We'll nudge those weights and biases in a way that it reduces or minimizes our loss function. And that's what training means. So at the starting, those weights and biases were completely random. And after all the training, the machine has learned those correct values of weights and biases so that the loss function is minimized. So that's what training means. Perfect. So now we'll have a look at the whole forward pass in detail. Let's start with our neural network architecture that we are building in this particular video. So you can see we have two neurons in our input layer, one hidden layer and one output layer. Now, why two neurons is a simple reason, because you see the XOR gate, we have two numbers as input, 0, 0, 0, 1 and all that. That's why I chose two neurons. Now let's come to one of the most important parts, the parameters of our network. Those are weights and biases. Now you see, our network has many connections, but each connection is not equally important. So we wanted to assign weights to each connection. It basically says how important is that connection in determining our final output or in reducing the loss, right? So you can see it's W11 and W21, and similarly these two connections and the final this one, the V1 and V12. So these are the weights that I've assigned, and also you can see the bias as well, B1, B2, and in this case C. So the total parameters are 9 here, which are 6 weights and 3 biases. These are the parameters. Now, in the modern LLMs that you'll see, like GPT and other Claude, you'll see they have billions of parameters. So you can like get the sort of comparison here that in our network we have only 9, but the modern LLMs have billions or trillions of parameters which they train, right? Now let's start the forward pass. So we know the values of x1 and x2, which are the input values. Now how do we go to h1, right? For that, let's do this. Now to calculate the value of h1, we have to do 2 steps. Number 1 is this. So I'm considering, I'm considering this particular example of where the inputs are 1 and 1. Okay, so as you can see, x1 is 1, x2 is 1. Now we are going to h1. For that, we'll multiply the input and its weight, x2 and with its weight. And with that, we'll also add the bias. And this is a very common question, that why do we add a bias? Now, simple way to understand this is that imagine the case where all our inputs are 0. In that case, our output will always remain 0 and the machine won't learn anything. That's why to tackle such cases, we have to add a bias to it as well. And while coding, I'll also show you that what if we remove the bias, how does our network behave? Okay. So this was our first step in calculating the value of h1. This is not h1, by the way. I've named it z1. Okay. And now next comes the next step, is where we're putting that z1 into another function. Now what function is this? This is a sigmoid function. Let me Google search it, right? So this is a sigmoid function, and you can see this looks like a S curve. And now let's focus properly. This particular function always gives us the value between 0 and 1. And it accepts the value, like the input value from like the whole real number line, but the output is always between 0 and 1. And see the function here. It's 1 by 1 plus e raised to negative x. Now let's do some math here. Let's imagine our input is 0. Put x is equals to 0. What do we get? It's 1 by 2, right? 1 by 2 is 0.5. So when x is 0, we get 0.5. You can see here, right here. Now let's imagine a large positive value for x. What do we get? It becomes 1 by 1 plus, and this value becomes 1 divided by e raised to some large number. And that would be tending towards 0. So the overall value tends towards 1. It will never become exactly 1, but it will reach or tending towards 1. And similarly for large negative input, it will tend towards 0. Okay, it will never reach 0. So I hope you get the sigmoid function. But yeah, that's a common question again, that why are we using a sigmoid function? Because our outputs could have been anywhere on the number line. So we wanted some definite range. That's why we use this. Now, let me tell you, this is called an activation function that we're using. And there are many common activation functions. As you can see the list here, ReLU, sigmoid, tanh, and softmax. These are very common activation functions that you'll see in many neural networks. For our particular case, I've chosen to use sigmoid function because it gives us a continuous S curve, which is also differentiable. So it will be easy for us. So this was step 2 in calculating h1, and whatever we get now is the value of h1, right? And now we'll do the same thing for calculating h2. So you can see the same input, but the weights have changed because the connection is different now. So we'll multiply it, add the bias. This gives us z2, and now put this inside the sigmoid function, and we get the value of h2. And now once we have the values in our hidden layer, I'll call it layer 1, we can ignore our input layer, right? So now we can only look at this part of the network. Now let's do the forward pass here as well. Now imagine h1 and h2 as the input layer and y is the next layer. Now you know what to do next, right? We'll multiply h1 with v1 and we'll multiply h2 with v2, and we'll add them, and we'll also add the bias, which will give us some value z3. Okay, so this gives, let's say 0.89, and now we'll put that inside sigmoid function, which will give us the value of y, and that is going to be our machine's guess, right? I told you earlier that we'll allow machine to take a random guess. This y value is the machine's guess. And why it's random? Because right now the weights were totally random. I didn't select 1.2, negative 0.5 and all. This were absolutely random, even the biases as well. So let's go to the next step. As you can see, this is the machine's guess 0.7. But if you see properly, and we have chosen this example, right? 1 and 1. The correct output was 0, but machine guessed it as 0.7. So there is definitely some loss. And how do we calculate loss? So we calculate it by y minus t. Y is machine's guess, t is the target value. And we square it. And that gives us the loss. Now, why are we squaring it? Because it's a simple thing. Because let's say we get, let's say, okay, just a minute. Okay, so the question was, why do we square it? It's simple reason, because let's say one input gives us plus x loss and the other input gives us negative x. And if we won't square it, the overall loss would become 0, and we don't want that. So to get rid of that negative sign, we square it, right? So in this case, this is the difference, and once we square it, we get the loss as 0.5. Now this was the forward pass for only one input, right? We'll repeat the same thing for all the 4 inputs, and we'll sum it up. So that gives us the final loss. Okay. Now what is our goal? Now we'll back propagate. So this was forward pass. Now we'll go in the back direction, and now we'll nudge this value. So now you know what are we nudging, right? We are nudging these weights and the biases so that our loss is minimized. That is going to be our next step. Now let's have a look at the code as well of the forward pass. So I've written the forward pass here. Have a look. The data is defined like this. Now let me tell you, in generally we describe data and our weights in the form of matrix or in form of tensors. But right now we only had 4 inputs and 9 parameters. So I thought it's easier to put it in simple list format. And also this video is for beginners, so list is simple for you to understand. So this is our input. It's a list of tuples. Each tuple contains the input numbers and the target value. Now keys are, now I hope you can recognize these variables. These are nothing but the parameters of our network. Now here I'm writing the forward pass. Let's see. First of all, I'm receiving p as the one of the parameter in my function. What is this? P stands for our parameter here only. So imagine this as a dictionary, a Python dictionary, where, just a minute, where the keys are the weights and biases, and the value is going to be, let's say, the random value 0.3. And similarly, we'll have all the keys of all the weights and biases, right? So this is P. Now let's calculate H1. So for H1, what we are going to do? So for H1, what we are doing is multiply the weight and the input, add the bias, and put this whole value inside a sigmoid function. And as you can see, the sigmoid function I've already defined here. It is 1 over 1 plus exponent e raised to negative z, right? Similarly, we have H2 and we have Y. I'm not explaining this again because I hope you understood it pretty well from the diagram, and it's easy to follow right now, I guess. So this was our whole forward pass, and now will come the most important part of this particular video, which is back propagation, where we'll nudge these values to minimize our loss. Let's do this. Okay, I'll choose. Okay, this is nice. This is nice. And also, I've turned on the ring light. I should have done it earlier. I just don't mind the circle. It's from the ring light. Okay. Let's go to back propagation now. Very important, most important part of the video. Let's go back to our network. Now, so I have to minimize this loss, and for that I'll change these values, or I'll change all my parameters. But how do I know that whether I should increase it or decrease it? And that's where calculus will help us. So we'll calculate how sensitive our loss function is with respect to V1 and with respect to all the parameters. That's the goal in back propagation. And once I know that what's the relation between my weight and the loss, then I can change it. So this is called gradient descent, and it will tell me 2 things, right? What are those 2 things? It will tell me the direction and it will tell me the magnitude. So I know whether I should increase or decrease it, and also how much should I nudge it. So I'll get these 2 set of information from gradient. So let's start with V1. In order to calculate how V1 changes my loss function, I cannot do it directly. Because I'll show you the chain here, chain rule, right? Look at the chain here. V1 is directly linked with Z3 and Z3 is linked with Y and Y to L. What I want is relation between L and V1, but there are some like different variables in between. So I cannot get it directly. That's why I have to use chain rule. So the first step would be calculate the relation between Y and L. So how loss function changes with respect to Y. I will multiply it with how Y changes with Z3. So this is what this gets us. And then finally how Z3 changes with V1. And the DAO symbol is you're using because we are doing partial differentiation. We're doing it with respect to a single variable. If you have done multivariable calculus, you would know. But I hope you get the idea of differentiation. In differentiation, we are basically calculating the rate of change with one variable with respect to another. Okay. So let's calculate these values, right? So first I need dou L by dou Y. This was the relation between, like this was the equation between them. Let's differentiate it. Now, when differentiating with respect to Y, t will be constant. Okay. Now it's a simple exponential like x to the power n, which becomes n times x raised to n minus 1. That's what we have done here. And this is the differentiation. Let's move on to this one. This is the equation between Z3 and Y. We have to differentiate Y with respect to Z3. And we get this. How did we get this? So let's go to the differentiation of sigmoid function. I just Google searched it. And basically we'll have to apply chain rule here as well, right? And I guess we can use the division rule and all of that. Yeah, it's a simple one. So you can follow the steps here, which ultimately gives us this as the answer. So the differentiation of sigmoid function with respect to x would give us sigma x times 1 minus sigma x. And that's why here we have y times 1 minus y. It's a simple differentiation. I'm leaving it to you guys. I think you can do this. Next comes this part. This is the equation between Z3 and V1. Now, since I'm differentiating with V1, this whole thing would be considered as constant values. And that's why the differentiation only gives me h1. And this is constant, so it is basically plus 0 here, h1 plus 0. Right? These are fixed numbers. So I hope you get this. So now let's move on to V2. Right? Now what changes here? The sequence is almost same or exactly same here. Just V1 and now we have V2. So this part remains same. This also remains same. But now here we have h2 instead of h1. So to make things simple, what I'll do, because these two expressions are same in both the cases, I'll multiply them together and I'll call it delta out. So let's go back to this network, right? Let's get to the backpropagation. I calculated this dl by dy, and that's what I was talking about, delta out. So because these two expressions were common in all the three cases of v1, v2 and the bias, so let's take this as a single quantity. Now in order to calculate these three, it's going to be a simple task. Just multiply delta out with h1 for v2 multiplied by h2, and for our bias we are multiplying it by 1. Why? I'll show you here. In the chain rule, if I go to our bias here, when differentiating with respect to c, these expressions become constant, so they give 0, and for c we only get 1. Okay, so this was the differentiation. This was the relation between our loss function and v1, and like basically how sensitive our loss function is with respect to v1, v2 and our bias c. Perfect. So we have done the half part. Now we have to go back one more layer and calculate the differentiations with respect to these weights and biases. So again, we'll apply the same chain rule, but definitely the chain is going to be longer now. So as you can see, this is how the chain looks like. We get the z1, then h1, and now z3, y and l. If you see, the later part is almost same. It is exactly same. We have already covered this. So now we only have to deal with h1, z1, and then finally to w11, right? So we calculated this, okay, and we also calculated this, and we multiplied both of them, and we called it delta out. Perfect, right? Look at the chain here. We need to know how z3 changes with h1. Okay, so that's what we are doing here, and we this gives us v1. Perfect. Let's move on. Again, we have a sigmoid function, but now between h1 and z1. But the pattern is same, that we get h1 times 1 minus h1. And now the final step where we get the relation between z1 and w11. We'll treat this as constant, so we get x1. Perfect. So to make this simple, we already know these two equations. We multiplied it, we called it delta out. Now for one particular path, we have these v1 and this h1. In the other path, we'll have v2 and h2 here. So that's the only difference, right? So let's go back to tracing example. So now we already saw this. We multiplied delta out with v1, and I told you there are two paths, right? So one is v1, other one is v2. Now in the next step comes the h1, right? This is path 1, so I'm calling it delta 1. And the other path will deal with h2, delta 2. And now things are simple. So w11, w12 and b1, we just have to multiply it with x1, x2 and 1. And for w21, w22 and b2, we'll have to multiply it the same inputs, but now with delta 2. And here we have. So we now, good news is we have the relation between all the parameters with respect to the loss function. So I'll repeat this again, that we now we know two things. One is like what direction we should nudge in and how much. So we know the magnitude as well. Okay. So how does the nudging part looks like? And in that we have one more very important variable, which is called the learning rate. So how fast we want the machine should learn. That's the learning rate, right? I'll show you the math behind it. So now comes the nudging part, and only thing that you need to know is this particular thing. So we know the old value, now we have to change the old value. So we are multiplying with a negative sign, and then we are doing learning rate times the gradient. So I hope you know the gradient, right? How it's related with my loss function. I know the direction and the magnitude, but I'm deciding how fast should I learn it. But the important thing is, what does negative mean here? So let's see here. So let's say we have this particular relation between loss function and w1, and what the value we got was a positive value. Now what does it mean? It means if I increase the value of w11, my loss will increase, right? And similarly, you can see I see some positive values here. Let me check other example. Okay, here we have negative 1. So w21 says the relation is negative. It means if I decrease w21, then loss will increase. But we have to do the exact opposite of this. What we want the loss to decrease, right? So in this example, where the relation is positive, we'll put the negative sign because we'll make sure the loss decreases. I hope you get the idea now. That's why the negative signs comes in. And let's go back to step size here. Okay. So this is what we are doing. So this is the way to nudge our values. Old value, negative learning rate times the gradient. And this gives us the new value of our parameters, and we'll do the same for all the 9 parameters. And the fun part is, and the crazy part, right? This whole forward and backward propagation for all the 4 inputs, this whole thing together becomes one full run, or we call it one epoch, right? So we went forward and backward for all the 4 inputs. In our some other neural networks, we can have hundreds or thousands or millions of input data. So doing this whole cycle becomes one epoch, and we do multiple epochs. We do probably thousands of epochs to train, because this gives some time for our network to learn the correct weights and biases. So I hope you understood how neural network is learning. So basically what we'll keep doing is we'll keep changing the weights and whether our loss is decreasing or not. Now let's have a quick look at the code. I'm not interested in going into detail, because if you understood what I explained to you earlier, writing code would be a cakewalk for all of you, right? So this is the backward function where, okay, so now you can recognize these variables, delta out, delta 1, delta 2. And ultimately what we are returning is this particular dictionary. So we are returning 2 things. So this thing is a dictionary where we are returning the gradients of each of the parameters. And also, if you remember, this was our loss function, right? So this is the total loss. y minus t whole squared. Okay, so this is the backward function. So we'll call it, we'll just go forward and we'll calculate the gradient descents, the gradients. Okay, now, so now time to combine the whole thing together and run our program. So let's start with P. So I already told you P is our dictionary of all the parameters, and we are starting at random values between -1 and 1. So for K in keys, as you remember, these were my keys, and I'm initializing at random values. And this is LR, this is my learning rate. Okay, I'll also write it. Perfect. Now for epoch, so now you remember this term. Now I'm doing the whole cycles. So I'm doing that for 60,000, but I'll tell you, in this case, we don't need these many epochs because I think network would be able to learn it much before 60,000. Okay. So this is the gradients. We are putting the gradients at 0 and the loss is 0. Now comes at this loop where for each of the input data, we'll do the backward, right? For each of the input data, we'll go forward and backward. And the backward function is returning two things. It's the first one is G, which is the dictionary of all the gradients, and second one is loss. And for each of the input, we'll keep adding the loss. Okay, and now we'll also keep adding up the gradients for the particular parameter. So for all the 4 inputs, we have added up the loss function or the total loss value, and we have added up the gradients of each of the parameters. And now once we have this data, we can come back here and make the changes. So this is the point where we are nudging, right? So in our weights, in our parameter dictionary, what we are doing, so you remember we are doing old value minus learning rate times the gradient. And basically what we are doing is we are taking the average of it, because earlier what we did was we took the sum of all the 4 inputs. So we wanted the average of all the 4. Here the length of data is basically 4. So this gives us the average gradient of our parameter K, right? K could be W11, W12 and all of that. And we multiply it by learning rate. So this was the nudging part, and that's it. So now I'm just writing the final output here in this particular format. This is simple. So once we do all this, once we do one run for all the 4 inputs, we again put our gradients at 0 and loss at 0, and then we'll run our another epoch, right? And we are running this. So let's see the results here. So at the epoch 0, the loss was 0.27, and this was machine's guess. Okay, the target values that we were expecting was 0, 1, 0, 1, 1, 0, but the answer came was 0, 0, 0, 0. I rounded off these values, the raw values I rounded off, and this is the answer, but the target was this. After 1000 epoch, the loss decreased to 0.23. This was machine's guess, and as you can see, we are closer to the target value. We got like 4 out of 3 are correct here, but still this is not a good guess, right? Not a confident guess. But now once we get to 10,000, now you can see some confidence, right? This is really close to 0, and these values are actually much closer to 1 compared to these values. So now you can see our answer and target value are matching. So we can actually stop right here. We don't need to go to 60,000 epochs, but I already did it, right? So this was a neural network. I hope all of you understood it. And if you have any doubt, let me know. Or if you have any suggestions, please let me know in the comment box below. So the interesting part, or the fascinating part that we must appreciate here, is that we didn't write the rules of how an XOR function looks like, or how an XOR logic gate looks like. We just provided the data, and machine or our neural network learned it on its own. And just, it was like a simple feedback loop, right? You try something, you get the feedback, and you make some changes, and you try again and again, and you do it for thousands of times, and eventually you get it. Eventually you learn the pattern. Okay, so this was fun. I enjoyed it, and I'm planning many more videos on this channel about related topics. We'll go into much more detail. So this was a video for absolute beginners. Now there are many things after this. There is CNN, there is STLM, and then transformers, attention, and the LLM thing, everything, right? So I am interested in teaching all those concepts as well. Feel free to like and subscribe if you loved it. The main motive was to get you introduced to this topic, and I hope you liked it. I guess I would end with that and see you in the next video. Thank you very much. Bye bye.